Have you ever thought about how oil companies are just going around and continuously fracking? I mean, sure, it may be necessary for them to frack sometimes, but maybe these companies should show some decency and frack a little less. It's being done all across the globe, and to be honest, we can only frack the earth so many times. Fracking, or known technically as hydraulic reservoir stimulation, is a process used to extract oil from non-permeable geological formations. Basically, oil can sometimes become trapped inside rock structures. The oil can then be released by pumping liquids under very high pressures through connecting wells. The pressurized liquids crack or fracture the rock enclosure, allowing for trapped oil to escape. Though the fracking is effective in freeing oil, the process produces a lot of waste, however, called oil field wastewater.
Oilfield wastewater is a fluid. It's a water that is co-produced with oil and gas, which means that when oil and gas is recovered, a certain percentage of the product that comes out of the ground is actually this oilfield wastewater. It's a brine.
That is Dr. Ryan Pollier, an assistant professor in geosciences from Virginia Tech.
So it's a water similar to seawater, except where seawater has maybe a concentration of about 30,000 parts per million of dissolved solids. This brine that comes up with the oil and gas has 175 to 200,000 parts per million dissolved solids. So this water that comes up with the oil and gas is effectively toxic to terrestrial ecosystems, and it's considered a waste, and so it's disposed of that way.
The waste is disposed of in wastewater ejection wells, which run a couple of kilometers down into the earth, far below our freshwater reservoirs, thank goodness. Pumping oil waste into the ground does not sound like it comes without consequence. If it isn't dirty drinking water, then what is the real issue?
Pumping this wastewater underground increases the fluid pressure. And so what that means is that the volume of water that's down there, the naturally occurring fluids, is there. And when we add more fluid to it through this wastewater injection, we increase the fluid pressure.
This pressure buildup occurs in pools. The deeper you dive, the more pressure you feel from the water above you. Since this wastewater is also more dense than regular water, it has more mass in the same area, meaning there is even more pressure buildup at the bottom of the reserve as more wastewater is pumped in, which is not good news.
That fluid pressure actually kind of migrates away from the injection wells, and then as it does so, it can destabilize faults. And one of the primary consequences that we've been dealing with in the area of oil field wastewater disposal are what we call injection-induced earthquakes, meaning the fluid pressure from the injection destabilizes faults and causes earthquakes.
These induced earthquakes are very similar to those from tectonic plates in terms of their size. The good news, the overall number of earthquakes has been going down in the past years. The bad news, though, the intensity of these less frequent earthquakes has increased, as Dr. Chapman, a research professor from Virginia Tech, can explain.
Well, what we've seen is that there's been an increase in magnitude 4 earthquakes dramatically here in the last few years. A magnitude 4 earthquake is about 10 times bigger in terms of the amplitude of the ground motion than a magnitude 3, and 100 times bigger than a magnitude 2.
And 1,000 times bigger than a magnitude 1. I'm still a little confused, though. Surely it would be better to have fewer earthquakes, even if they are larger, right? A single bee is no issue, but a whole swarming nest is a force to be reckoned with. Is it not the same concept?
It only takes one large earthquake to cause substantial damage. The analogy would be to think about, and I grew up in Southern California, and so in Southern California, we feel the smaller magnitude earthquakes all the time, right? The magnitude 3s, the chandelier just kind of starts moving side to side a little bit, and like, oh, there was an earthquake, neat, right? But then in 1994, when the Northridge earthquake hit, that was a big earthquake. It did a lot of damage, both economically and in terms of human health and safety. And so I think that's a very real concern for real damage if there's that one large earthquake.
The next step for Ryan and Martin is to look at the bigger picture, creating a simulated model that can accurately predict how liquid density changes underground pressures, which then stimulate increases in earthquake intensity. Specifically, they want to model the hazard associated with these pressure changes.
Now, if we can model how the hazard is changing, then what we can do is that information can be passed over to the civil engineers and the city planners and the people that make decisions about how to handle infrastructure in the context of ground shaking and ground motion. And then it becomes, a public policy question of what are we going to do about this? Are we going to start retrofitting buildings in affected areas? And I can tell you that I know in Oklahoma that has been a bit of an issue. That's been a contentious discussion that's been had in the last several years, right? Making decisions based on good research and good science is, I think, a very admirable goal for all of us.
Ryan Pollier and Martin Chapman speaking about their work published in the journal Nature Communications.
Music in the program is sponsored by Epidemic Sounds, perfect music for audio and video productions.